Hello again, we continue with differentiation rules. This time we want to learn about the sum rule and the difference rule. So we're going to consider a function y equals f of x plus g of x, and we're going to try to find the derivative of the sum of these two functions. So I'm going to say y prime is equal to the limit of f at x plus h plus g at x plus h minus f of x plus g of x, okay, all over h when h approaches 0, according to the definition of a function, or of the derivative of a function. Okay, now I can rearrange the terms a little bit in the numerator, so I can rewrite this as limit of f at x plus h minus f of x, and then plus g of x plus h minus g of x all over h when h approaches 0. And we see that this is a big fraction. I can split it up into two fractions because I have a common denominator of h. And then I can use the properties of limits which we have studied long time ago. I can say limit of sum of two functions equals to the sum of the limits of those two functions. So I'll write limit of f at x plus h minus f of x over h when h approaches 0. This is the limit of the first function plus the limit of the second function, okay, when h approaches 0. So limit of sum of two functions. This is the first function, f at x plus h minus f of x over h. The second function is g of x plus h minus g of x over h again. Now the sum of those two functions, when you want to take the limit, you're going to say limit of sum equals sum of the limits. So it will be limit of the first fraction plus the limit of the second fraction. So here we are splitting up this big fraction into two fractions, and then we argue that limit of sum of those two fractions equals to the sum of the limits of those two fractions. Now this first limit is very famous. You have seen this many times. That is actually f prime of x, and this second one is also g prime of x. So for y equals f of x plus g of x, we showed that y prime is actually equal to f prime of x plus g prime of x. In other words, the derivative of sum of two functions equals to the sum of the derivatives of those two functions. And you can extend this idea for like 200 functions as well, for n functions. So I may write down here that y equals f plus g plus dot dot dot, which means that if you have like more than two functions in addition form, 3 functions, 4 functions, 10 functions, then the derivative of that sum would be the sum of the derivatives of those functions. That's what I can write here. Okay, so these are the rules from before, and this is the fourth differentiation rule we are learning now. Okay, the story of the difference rule is not very different from the sum rule. Basically, it's the same thing, except that instead of addition, we just have to subtract the two functions. So perhaps I can fix this. I can say this is minus instead of plus. We have a difference of two functions, and then this would be difference, this would be difference, and then this would be minus, and this minus would not change. Negative times negative is positive, so this becomes positive right here. And then I would say this one doesn't change. This one, if you factor negative sign outside, that becomes negative, this becomes negative. And as a result, we end up with minus here. So the proof is just the same. You just have to adjust the plus minus signs properly. And we're saying y is f of x minus g of x, and y prime is f prime of x minus g prime of x. That's what we're saying here. And it's called difference rule. The proof is very similar. Why would I bother rewriting the whole thing when I can easily adjust the plus minus signs? So y equals f minus g, or minus whatever. The derivative would be f prime minus g prime, and it can be extended for many functions. So now that we have learned A, B, C, D, E, we have learned 5 differentiation rules. There's more coming down the pipe. I promised 10. So with these 5 differentiation rules, why don't I give you some examples here? Okay. So we have a function in the form of x squared plus 6x. I want to find the derivative. So first of all, this is in the form of sum of 2 functions, one quadratic function, one linear function. So we said that the derivative of sum equals sum of derivatives. So all you have to do is to take the derivative of each one of these functions separately, one by one, and add the derivatives up at the end. What is the derivative of x squared? Well, you have to apply the power rule of the derivatives. So that would be 2x. And derivative of 6x, well, you have to apply the constant multiple, because 6 is a constant times derivative of x. Derivative of x is 1. So 6 times 1 is 6. So the final answer is going to be 6, and that is the final answer. More examples. 8x cubed minus 4x squared plus 6x minus 1. So we have a whole bunch of functions in the form of addition subtraction. Okay. So according to the sum and difference rule we just learned, we can differentiate each term separately one by one and add or subtract the final results. Derivative of 8x cubed, well, we have to use the constant multiple rule. Here the constant is 8. So whatever the derivative of x cubed is, according to the power rule, which is 3x squared, we're going to multiply that by 8. So 3 times 8, 24x squared minus 8x for the same reason, 6. And derivative of negative 1 is 0 because of the very first rule we learned. Negative 1 is a constant. Derivative of all the constants is 0. I'll give you more examples. Y equals x, or actually square root of x, minus 6x to the 10 plus pi x minus 4 pi. Okay. So here we have square root of x. You know that square root of x can be written as actually x to the power of 1/2, right? And then we can apply the power rule. We can say the exponent is 1/2. So we said that n can be any real number, including a fraction, including a rational number such as 1/2. So it's going to be 1/2 times x to the exponent of 1/2 minus 1. So this would be 1/2 times x to the exponent of 1/2 minus 1 is negative 1/2. And then we have minus 60x to the 9 plus pi and then minus 0. Right? This is minus 0 because 4 pi, end of the day, is a constant if you think about it, right? So if you simplify, the answer would be 1 over 2 square root of x, expressing the answer as a radical, minus 60x to the 9 plus pi, final answer. Okay, so that was another example. Then I give you another example. Y equals 6 cube root of x minus 5 over x cubed. Okay, so before I differentiate, I'm going to write this with rational exponents. So x to the power 1/3 is the same as cube root of x. And then this would be negative 5 times x to the power of negative 3. We know the negative exponent law, right? Any number with a negative exponent equals to the reciprocal with a positive exponent. Therefore, I can write x to the power of negative 3 instead of 1 over x to the power of positive 3, right? So now I will differentiate. So 6 times 1/3 is going to be 2x to the exponent of 1/3 minus 1, which is negative 2/3. And then minus is plus 15x to the exponent of negative 4. Okay, that's the answer. But we never leave the answers with negative exponents, right? So this is going to be 2 over cube root of x squared, actually. If you convert it into radical form, you have to know the exponent laws, root laws, so many things, you know, because here in this course, there's no time to sit down and talk about the very basics. You need to know how to convert, rational exponents into radicals back and forth and so on and so forth. So 2 over cube root of x squared, and the other one is 15 over x to the exponent of 4. And that is the final answer for this question. So I gave you 4 examples, and I'm going to just wrap up with notations for the derivatives, which I forgot to mention it earlier. When you have f of x, y equals f of x, one notation is the prime notation, f prime of x, okay? Another notation is y prime, simply. Another notation is dy over dx, and this is known as Leibniz notation. So Leibniz, you know that Wilhelm Gottfried Leibniz was a German mathematician who is known as the founder of calculus along with Sir Isaac Newton. So this notation dy over dx is known as Leibniz notation. And what it is nothing but y prime. It's just a different notation. In high school, you're going to consider dy over dx as a package. We're not going to separate the numerator from the denominator. And we're going to say, okay, dy over dx means the derivative of y with respect to x. That's the meaning of it. This is the notation, and we accept it as a package, and it's equal to y prime. In some older textbooks, they use capital D operator notation. They write D sub x, which means derivative with respect to x, and that's another way to show the derivative of a function. It's not used in your textbook. In some older textbooks, that's the notation they use. It's called D operator notation. Mostly, you have to know dy over dx, Leibniz notation, and the prime notation, which was introduced by French mathematician Lagrange. So these are the notations we use. So instead of y prime, I could have said f prime of x, for example. Or instead of writing this, y prime equals this, I could have said dy over dx equals that answer, and so on and so forth. Okay, so in the next lecture, we'll talk about more differentiation rules. Thank you.